Okay, welcome back everyone for the second part of the introduction to density functional theory, and we will now discuss the Schrödinger equation and the Born-Oppenheimer approximation, starting with a comparison of classical versus quantum mechanics. So in classical mechanics we always have a continuous. So, for example, the kinetic energy, for each velocity, right, we get a kinetic energy value. So it's more like walking up a ramp. Whereas in quantum mechanics, our solutions are quantified. So it's more like a step function. And that's the main difference between classical and quantum mechanics. Quantum mechanics is not continuous. And the main equation here is the Schrödinger equation, which has the Hamiltonian of a given system in it, the state function, and then the energy as output, as a function of the state function again. And solving the Schrödinger equation, that's what we do in quantum mechanics. And that can be quite difficult, as I said in the introduction. Solving the Schrödinger equation later for many body system, as we do in physics or in chemistry, becomes a challenge. But let's start with a simple case where we can actually solve it to get an understanding how to use the Schrödinger equation. And the simplest case is the particle in the box. And if you have not done that, I would highly recommend everyone to solve the particle in the box. There are various books who has that exercise, and then there's also a follow-up problem, the harmonic oscillator, which is also worth to solve, just to get the feeling how to handle the Schrödinger equation, how to work with the Schrödinger equation, because that's what we do in the later process of that lecture. Okay, but coming back to the particle in the box. So the assumption is we have an electron in the potential well, like that one, with infinite volts. What does it mean? So basically that the potential is infinite outside on the left hand side of the potential, and also infinite on the right hand side of the potential. And it's zero in the within the potential energy regime. We need to set one more boundary conditions. The electron is only allowed to move within the potential, okay, and the state function must vanish for values smaller than x or larger than a. And for that reason, it needs to be zero basically at the edge cases, because if it's not defined as zero at the edge cases, we basically get a step function, and we don't want to do that. And how do we start now? So our Hamiltonian for the electron in the potential well looks like that. It's quite a simple Hamiltonian. And now we need also a state function, and for that we take a overall simple solution of a differential equation with two parameters a and b, which needs to be solved during the process. And if we do that, what we end up is an expression for the energy, which gives us energy values in quantum states. It depends on n, right? That's why it's also e as a function of n, and n is an integer counting from 1 up to infinite basically. And what does it mean is we get for n equal 1 energy value, and then for n equal 2 a second, and so on and so forth. But it's not a continuous energy spectra as we would expect for the classical mechanics. Instead it is a step function. And the solution for the state function looks similar. That's from Wikipedia. I like that animation. So A is the classical solution. if we would have a classical case, we would get a continuous energy solution. So that's why our particle is moving from left to right. Whereas in the quantum world, we get probabilities. And where does the probability, how do we express that? So for the n equal 1 case, the probability, or independent of the which state we're currently looking at, it's 0 as our boundary sets 0 at both edge cases, and then it becomes, for the n equal 1, maximum in between, and then for the n2 we have one not plane, and then for the n equal 3 case we have two not planes, and so on and so forth. So meaning that at the not plane, the probability, as you can see here, it's 0, and then on either side half the not way, it's basically maximum. And that's the state function solution for our particle in the box. So we can solve the Schrödinger equation, and it gives us that quantum state what we assumed in the beginning. But now, moving to material science, our Hamiltonian looks a bit more complicated than for the one-dimensional particle in the box case, and our time-independent and non-relativistic many-body Hamiltonian looks like the following. I would like to point out that for the rest of the lecture we're using atomistic units, meaning that we set h bar, the electron mass, as well as the electron charge, as well as the fraction here, to 1. You find the different, you might find the Hamiltonian in non-atomic units in other books, so just keep that in mind. And for any system, right, we have our core in the center, and then our electrons in shells surrounding the core. So how does then the many-body Hamiltonian look like? So we get a term for the kinetic energy for the electrons, meaning how fast do the electrons move. The same for the core. Then we got the potential for the electron-electron interaction. Oops, that's the kinetic for the core. That's the potential electron-electron. We get the potential for the core-core interaction, right? If we have two cores, then we get the interaction between those two cores. And we get the interaction between the electrons and the cores, because those also interact with each other. And we can solve that problem for hydrogen. But beyond hydrogen, solving the many-body Hamiltonian without practical implementations become quite a challenge. So one of the most common approximation to solve the many-body Hamiltonian is the Born-Oppenheimer approximation. I would like to point out that the Born-Oppenheimer approximation, sometimes also called adiabatic approximation, so you might find that one also in your books. And the idea is quite simple, because the electrons are way lighter than the nuclei, right? For the lightest core we can imagine, the hydrogen, the weight difference between the hydrogen core and its electron is approximately 1,800, and that number increases, right? For carbon, for example, an electron is 20,000 times lighter than the carbon nuclei. So the assumption of the Born-Oppenheimer approximation is that the electrons are moving in the fixed field of the nuclei. What does it mean in practice? Is basically when an electron is moving, the core doesn't realize something passed by. And for that reason, we can rewrite our Hamiltonian into basically two parts. So the first two elements here, also sometimes but quite barely called the nuclear Hamiltonian, which has the only pure coherent parts in it, so that's the kinetic energy of the nuclei again, and that's the potential of the nuclear-nuclear interaction, and then the electronic part of the Hamiltonian, composed out of the kinetic energy of the electrons, that one, the electron-nuclear interaction, as well as the electron-electron interaction. What does it mean in practice? We can split our Schrödinger equation into two parts, into an electronic part and a nuclear part, which makes solving the Schrödinger equation more simple because we have our electronic Schrödinger equation based on the electronic Hamiltonian, which we solve in a quantum manner, and we have the nuclei Hamiltonian. Please think that, or please note that the nuclei Schrödinger equation includes the eigenstates, the eigenvalues of the electronic Schrödinger equation. But that just as a side note. Mainly it depends the kinetic energy of the nuclei and the nuclear core interaction. And that one, the nuclei Schrödinger equation, we can solve classically. So we reduced our problem, we splitted our problem, right, into some parts which we can treat classically, and some part, the electronic part, we can't treat classically. So we reduce the complexity of our system. And something to keep in mind is that by doing that, by separating the nuclei movement from the movement of the electrons, we can also split the wave functions into this electronic part and the nuclei part. So that's the electronic part and that's the nuclear part. So in summary, what we end up is that our total energy, or the total solution of our Schrödinger equation, is split it into two parts. We have the solution for the electronic part, or the electronic contribution, and the nuclear contribution. So that helps us to solve the Schrödinger equation then in the later stage. So at that stage we discussed the Schrödinger equation and how to simplify it with the Born-Oppenheimer approximation to provide us with a practical possibility to solve it. And then in the next part we will discuss the electron density.